So our next speaker is Karinne Ramirez Amaro. She is an associate professor at Chalmers University of Technology in Sweden. Her research interests include interpretable and explainable AI, semantic representations, cause-based learning, methods, and collaborative robotics, and human activity recognition and understanding. She has received several awards, including the prize of an excellent doctoral thesis for female engineering students and the Google Anita Borg Award. In addition to being a great scientist, Karinne is already a great contributor to the community and RAS in particular. She's done too many things for me to list them all here. I suggest you look at her bio to see about them. Welcome, Karinne.
Thank you, Nancy. So, yes, thank you. Okay, thank you very much. It is my great pleasure to be here today, and I would like to explain you a little bit how we are combining interpretable and explainable methods for robot decision-making. So far, we have seen this kind of robots deployed already on warehouses, right? And the main challenge is, I'm wondering, how we've solved the problem of autonomy in robotics. I will argue that autonomous robots should learn from experience, because learning from experience will allow these kind of robots to adapt to new challenges and new changes in the environment, specifically when we are talking about this kind of dynamic systems. In order to learn from experience, the robots should know what it should be doing. Like, for example, in this case, the robot knows that it needs to pile up one set of boxes from one place to the other, and it knows the set of tasks that needs to be done in order to achieve that, right? The next challenge is, okay, how does the robot needs to do that? And this involves the robot knows what kind of movement it needs to do. And we have here some of the talks in the morning about this. And then the next thing is why. And this is a very important question, because this will allow the robot to understand what it's doing the way it's doing it, right? I will focus this talk due to time constraints to just explaining the how and the why, because I think they are really highly correlated with the interpretability and explainability of the methods we are using. So we are looking into long horizon tasks, and if we see an example, we see that we want to stack boxes, for example, right? Now the question is, how should we represent these long horizon tasks? One way is that we can split this long horizon task in subtasks, right? Like we have here, reach a box, grasping, lifting, etc. And then the next challenge is, okay, what should we do in order to learn how to split this task efficiently, and then we can transfer to a robot? And for this, I argue that we should use interpretable methods. And before getting into the details about what kind of interpretable methods I'm talking about, I will give the definition I use typically when I refer to these interpretable methods. So here you see it's an AI system. It's interpretable if it's possible to translate its working principles into human understandable outcomes, right? So without affecting the validity of the system. And this is very important. We don't want to sacrifice interpretability with robustness. And we are using decision trees because it's a very good interpretable method, and combined with first-order logic or description logics as well. And as you can see in this video, the system is actually able to segment automatically what the demonstrator is doing. On the background also is learning a set of operators that is allowing the robot to create a plan in order to execute the task that was demonstrated by the user. And these kind of interpretable methods give you actually a structure model, which is good, because this means that we are able to follow up what kind of steps is this system able to follow in order to achieve the task, right? So this is one of the advantages of interpretable methods. Another advantage is that these kind of methods will provide explanations in case something wrong happened. And we are working with robots, and robots will fail. Right? Now the question is, we have this example of a robot stacking cubes, right? The target is to stack a tower of 4 cubes. And as you can see in the video, the robot is actually succeeding until the last one. Actually, what was the problem of the error? Was it the last cube that caused the problem, or was something really earlier in the foundation of the cube tower? And this is one of the challenges we're investigating. How can the robot actually detect what caused the problem, especially when these errors occur in the future and not immediately? How do we detect these errors? How do we prevent these errors? Prediction is very important because this will allow prevention, because we want autonomous robots, right? And then inevitably, if the robot fails, it should provide explanations about what went wrong. So in this case, we are working with causal validation networks because it gives you a really nice structure. And also, as you can see in this video, the robot is able to predict that something is going to happen that is going to lead to a failure. And therefore, we're using this contrastive search to find out what kind of parameters need to be fixed at what time in order to succeed with the building tower problem, right? And as you can see here, the robot is able to predict and prevent this failure before it happens. So, which is very good. However, failures not only happen in execution times. Failures can also happen when we have an incomplete model. Like in this case, we can see that the human is demonstrating a new task, which is putting a plate inside of the drawer. So it's teaching how to open the drawer, how to place the thing inside. Now we query the system. Now you can see that the environment has changed. There is a chair in front of the drawer, and this will lead to an implausible plan to be executed. Why? Because the task cannot be fulfilled due to the pre-consequences of the drawer not being free, right? So in this case, because of the explainability, the system is able to explain to the user, hey, I'm not able to find a plan because I'm not able to open the drawer. And then the system is going to allow the user to identify what is the missing task that needs to be demonstrated by the user so that the human is actually teaching the correct missing task only, not the whole demonstration. And this actually is going to save a lot of time for us that is going to teaching the robot, right? So this is another way of seeing how the failures can be addressed. And we have seen so far that we have the long horizon tasks, and we are able to segment and recognize these tasks into subtasks. And we are able to use the causal validation networks, which is the explainability part, to actually interpret what went wrong, what is not. And what about execution? What about the robot execution? So this leads to a new challenge, a new way of seeing the task. Like in this case, we see exactly the same problem of stacking cubes, but now we are using a reinforcement learning algorithm to actually learn how to do the long horizon task. And as you can see here, the system is poorly learning how to do the whole task. But what about if instead of learning the whole task, we split the task into learning smaller policies? Now the challenge is, okay, how do we change these policies so the system is able to create a solution for the long horizon task? For this, what we're proposing is combining the reinforcement learning features with symbolic planning representations. That means that we're combining high-level and low-level representation, and what we are proposing is a new definition of NDP, which actually considers information about the context. In this sense, we are including operators, because these operators will allow the agent to interpret, okay, how does the environment look before I execute my policy? And then this is the precondition, and how the environment look after I execute the policy, that means the effect. This information about the context is going to shape how we do the reward function for this agent, right? So this is basically our new proposition for the new MDP. And as you can see now, the system or the robot is able to learn this long horizon task. I mean, it's really not that long, but for the RL is quite long. One important thing that we need to notice in this example is reinforcement learning, sometimes the policies are not optimal and they will fail. However, our system, because it's using these high-level representations, is able to, even if it fails, is going to try to find out what is the next policy that needs to be executed so that we can solve the long horizon task, the goal, right? So we have these two different examples. And so far, I've been talking about single tasks, because this is very challenging. But I will give you a brief overview of what I'm thinking about in the future. Like in our group, we're looking about collaborative tasks, and this involves having the human in the loop together with the robot. One of the main problems is communication. How much information should the robot give to the user, like explanations, how often, how detailed? And then the human, how should the human interact with the robot to actually demonstrate the missing step that was not in the plan? And then for a collaborative task, actually, you need to have coordination in the task. And we are talking about a robot and a human. They are both having different constraints. which tasks should the robot execute? Which tasks should the human execute? And this is a very challenging part. So to conclude, because I see Nancy is already here, I've explained you about a little bit how the interpretable methods are very good for giving you structured models. However, this is with a cost, because these abstractions will sacrifice some of the details you need for a low level. I have also explained you about explainability, which are very powerful to prevent and predict failures, for example. However, the model that we have is going to increase with the number of values that the system has. And I have also introduced you how we are combining these interpretable and explainable methods with our new proposition of the MDP, which is making the reinforcement learning a little bit tractable. Now the question is, since we're learning these policies independently, can we transfer these policies to a new domain? This is the challenge we're looking into right now. We have 2 interactive sessions on Wednesday and Thursday in the afternoon. If you want to know more about this, we will be presenting this. And of course, special thanks to all the students, collaborators, international collaborators, and an invitation to all of you to attend SII 2026, which is going to be in Cancun in January. Thank you.
Thank you. So we can take a couple questions while we are setting up our next speaker. There's one hand right there.
Okay, thanks for the interesting talk. How important is understanding physics in the whole process? Because you have mostly observations, but if you stack blocks, it's important to understand how heavy they are and so on.
Exactly. And that's basically what we want to do with the reinforcement learning. So now that we have the policies, we want to add more information about the physics, like friction, forces in Mars, etc. We haven't done that yet, but we think that we are able to add that as a precondition or postcondition of the operator. Yes. Thank you, Darius.
Is there another question? There is one? Okay.
Somewhere.
Go for it.
Yes.
Yeah. So you talked a lot about explainability, but could you talk a bit about the modeling and the importance of how you model the environment? For example, I would guess in the block environment, some grad students spent a lot of time doing some good old-fashioned engineering to model the world as blocks that you can pick in place.
Yes. So we have the modeling of the environment differently. So for the causality, we have different variables like the height, the size of the cube, color, for example. We know the color should not be included into the causal model. And this is one of the things we see the system learning, that this is not creating a cause. We have the XY position of the cube, dimension of the cube. And for the reinforcement learning, the way we are modeling the environment is we have velocity positions of the end effector. We have the gripper open or close, in this sense. Yes.
Let's do it now. Yeah. Okay, well, thank you, Karinne.